All right, everybody. Today we're going to talk about optimization. So, what exactly is optimization? Well, sometimes we might want to optimize what's going on in our business. So, for instance, as we look at stuff like, let's just say revenue. Okay, when I want to look at revenue, do I want a lot of revenue that's money in, or do I want not a lot of revenue? Okay. And most people would say, well, if I'm in business, I probably want a lot of revenue, right? So we probably want to maximize revenue. Although we will see an example today, I believe, where maximizing the revenue doesn't necessarily maximize the profit. And what we really want is to maximize profit, right? We want the most money left in our pocket possible. Maximize the profit. Okay. Remembering, if you will, that profit is equal to the money in minus the money out, right? Money in, money I bring in minus money that goes out. Okay. And remembering we've talked about cost functions before. We've talked about, okay, you have to pay your workers, you have to pay your rent. Some costs are fixed, some costs are variable, right? So we've talked about all of those kinds of things. So what we want is this is money that stays in my pocket, right? And I would like, as a business owner, if I were going to own a business, I would like for the money that stays in my pocket to be maximized, right? So that would be maximum profit. Okay. And most of the time, I mean, most people would say, okay, well, I want to maximize both of those things. And in particular, money that stays in my pocket, I definitely want to maximize that. Although, what I started to say is sometimes maximizing your revenue might not maximize your profit. So we'll see an example of that today. I think it's today that we'll have to kind of go, let's see. What I really care about is the money that stays in my pocket. And then what about costs? Do we want to maximize costs? No, Dr. Webster. Okay, we want to minimize costs, right? Okay. So the idea here being that most of the time, if I can maximize the money coming in and I can minimize the costs going out at the same time, that normally leaves me bigger profit in my pocket, right? And that's kind of the idea here. So that's called optimal. Okay. Optimization is coming up with the optimal amount of money or the optimal. We'll see some different examples. The first one we're going to do is like a perimeter problem, so we need to optimize what's going on there. So that's called optimization. But in business in particular, these are the three things that normally we're trying to optimize. We're either maximizing revenue, maximizing profit, or minimizing costs. And we know, because we've already looked at this somewhat, that we might have things that look like this, right? So maxes are there and mins are there. But sometimes, like I said, with profit, my cost function may be rising. My revenue function might look something like that. Okay. And I might be trying to find somewhere in the middle of all of this, okay, um, where I can get the largest income while, I mean, here's the maximum on the revenue, right? But is that the best spot? Is that the most difference? What I'm looking for is the largest gap between these two, right? Because if I can come here and have low costs but high revenue, that's probably the best money in my pocket, right? The best profit. Okay. Whereas right here, we had some stuff we talked about earlier in the semester that were break even points, right? This was the point where my revenue equals my cost. Okay. So this point my revenue equals my cost, that point my revenue equals my cost. And those are good points to know because those are my break even points. But what I really want is the most revenue with the least cost, right? So where can I maximize my profit? That's what we're looking for. All right. So that's kind of the idea that's going on here. And that would be my optimal, if you would, place for my business to operate, right? And like small cost, big revenue, big profit. That's what I'm after. All right. So we will see in a little bit when we start talking about these business applications, that we're going to start talking about costs and revenues and profits and stuff like that. We'll see those things in there. But sometimes we don't know the function going in. So we kind of sometimes have to deal with, okay, this is just a word problem type thing, right? So what if I don't know the equation going in? Well, if I don't know the equation going in, I'm going to have to come up with one, right? Make one up. Now, I want to make one up properly. I don't want to just pull a rabbit out of the hat, right? But so sometimes we're going to have to come up and go, okay, how can I deal with that? And that's where, if you'll remember when we were talking about, okay, costs and stuff like that, the fixed costs, the variable costs, somebody in the back office somewhere is keeping track of how much are we paying our employees? Somebody's keeping track of how much are the costs for us to make that, whatever it is, DVR player or set of headphones or whatever it is we're doing. Somebody's keeping up with all those costs. What are my materials costs? What are my utilities costs? And somebody has to make up the equation, right? And that's kind of a little bit tougher step. That's more for the finance people or more for maybe the marketing people to come up with that kind of thing. But we're going to do a tiny bit of that. But the things that we're going to do to make up the equation are not necessarily going to be finance things. We're going to look more kind of concrete. So here's an example. So we're going to go back to some algebra type thoughts for a minute, and then we'll work into, okay, so what does that look like for business? So don't tune me out. You kind of need to know what I'm talking about here so that we can move forward. Okay. So I told you, word problem. A homeowner has $320 to fence a rectangular garden. Okay, we should understand this. Many of us are on a budget, and this is all the homeowner has to spend. They're going to um, only give me $320. So that's called a constraint. Okay, so I have to figure out how much fencing I can come up with without going over my budget. I'm being constrained or restrained by that budget. Okay, here's what we're going to do. 3 sides of the rectangle. Okay, hang on for a second. I'm assuming everybody knows what a rectangle is. So just to make sure we all know, let me draw you a little picture here. Okay, a rectangle has 90-degree angles, and the opposite sides have congruent measure, right? I'm putting those little hashtags. That just tells you these have the same measure and these have the same measure. Okay, so 3 sides of the rectangle are going to use 3 sides of the fence. We'll use fence material that costs $2 to $0.002 per linear foot. I actually had somebody in one of my class one time that was like, hey, that's actually what my business is. I do fencing. So there you go. Okay. The fourth side will use a wood that costs $6 per linear foot. Okay. And I'm using this word linear foot, this phrase linear foot. What does that mean? Linear foot means, okay, if this length, linear, this line here, okay, if this length were, say, 10 feet, okay, then that would be 10 linear feet. That's the length. Okay. So it means it's in the line. It's not giving me the vertical on the fence. In other words, you're going to figure out, okay, do I want a 3 foot tall fence? Do I want a 4 foot tall fence, a 5 foot tall fence, whatever. So these people have already determined how tall they want it. All we want to know is how long they want it. And that's where the linear foot comes. That's a line's worth of foot, basically, of feet. Okay. So we want to find the dimensions of the fence. Okay. So what's the lengths? What's the widths? That's what we're after, right? This is length, this is width. Those are the same. These are the same. Length, width. Okay. So find the dimensions. That's what they mean. Find the lengths and the widths. And the area of the largest garden that can be enclosed. Okay. Now, here's what I just heard whenever I read that out loud. I want the largest garden that can be enclosed. That's the wording that I'm looking for here. So when I go to optimize this thing, what they're telling me is I want to optimize or maximize the area. Does everybody agree with that? So they want maximum area. And that makes sense, right? If you were going to fence in a garden, wouldn't you want the most area possible inside of that fence so that you could have, oh, excuse me, the largest garden possible? I think most people would. Okay. So what they're saying is three sides are going to be out of this $2 material, right? And one side is going to be out of the $6 material. And probably they want a shorter side to be the $6 material. We'll find out for sure as we go along. But three sides are going to be the one fencing, and the other side is going to be the more expensive, the $6 fencing. Okay, that's the layout for this particular problem. All right, so we have to deal with a couple of equations here, and there's a little bit of assumption that we all know some of these equations. So hopefully you've dealt with some rectangle stuff before. Like I said, we're coming back to some of your algebra basics, maybe. Okay, so when you deal with a rectangle, I'm going to ask some questions. Hopefully you can answer them. If I wanted the area of that rectangle, what is the formula for finding the area of this rectangle? Length times width, Dr. Webster. That is correct. That's what I hear in my head. Okay. So whenever we talk about maximizing this particular equation, well, we're going to maximize it, but we have some constraints, right? So we only can spend the money on this fencing that I have. And the constraint was $320, right? Well, when I put this line of fence and this fence and this fence and this fence, I'm not measuring out the linear footage here is not the area. The area is the space inside, right? That's the area. Okay. What we want to know, we want to maximize that area while we constrain this to $320 worth of fencing material, right? Okay. What is this? The outside edge of this is where I'm going to put my fence. The outside edge is called the perimeter. Okay. The perimeter of this guy. Okay. So, how do I figure out the perimeter? That becomes the next question. Well, the perimeter is just simply length plus width plus length plus width. Okay. Or if you know that formula, it's 2 lengths, right? We're adding them all together to get the outside edging here. So 2 lengths plus 2 widths. And that is the formula that comes for perimeter of a rectangle. Okay. So we're going to have to play with both of those things before we can do anything about it. But first, we want to know that everybody has those two formulas somewhere in your brains. Hopefully you do. All right. So now what I'd like to do is just take a second and I'd like to talk about the cost function. Okay, the cost that's going on here. So this is something we haven't done before, right? We haven't figured out that cost function. So what they're saying is we're going to, let me get my picture back up here, pick a side. It doesn't matter if I pick the wrong side, that I'll come back and fix it later. It really doesn't matter. But pick one of these sides is my $6 side, right? And the other 3 sides are my $2 sides. So I'm going to say, and for no reason at all, I'm just picking one. I'm going to make this side on the left be my $2 side. I'm going to make this side be, left is my $6 side. Down here is my $2. Over here on the right, I'm making that a $2. And up on top, I'm making that a $2. Now, I'm putting it as one of the links, but if it doesn't end up being one of the links, it'll all come out in the wash whenever I get my answer. It'll be one of the widths. I don't care which one it is. We'll figure it out later. Okay. So this is the kind of thing that's going on. So whenever I start talking about my cost function, I've got something here that I say, oh, well, if this length here, say it was 10 feet, I think I said that earlier, and it's $6 per foot, then how much would that cost me? 10 times 6 would be $60, right? How did we get that? We multiplied the price times the length. Does that make sense? So it's the price times the length. Okay. For not just one side, but all 4 sides, right? So I've got a different price for the other length. And then for the widths, I have yet a different price for that as well. And does everybody agree that when I multiply these together, price times the width, I'm going to then turn around and add that together. So let's think about that for just a minute. Let me finish writing this. So price times width. Okay. So what I'm saying is the total cost is going to be however much this side costs, plus however much this side costs, plus however much this side costs, plus however much this side costs, right? Okay. And then what was the maximum I'm willing to pay? $320, right? So the cost here was $320. And that was one side was 6, so 6L, plus the other 3 sides were all 2. So I've got a 2L, a 2W, and a 2W. There we agree? Because these prices were 2 and this price was 6. And again, I just randomly picked the 6. It could be any of those sides. It does not matter. Okay. So let me clean that up just a little bit. I know that 320, that's the most my owner is willing to pay for me to build this fence. I've got a 6L plus a 2L plus 2W, and 2W is 4W. That is my cost function that I'm working with. Okay, so that's considered the constraint, and we want to maximize the area that we're dealing with. Okay, now the problem that we're going to have here is that we've got more than one variable going on here, and we also, don't forget, we also have to talk about the area equals length times width. And when I want to take, okay, let's think about this. I want to maximize this area, right? Okay, that's what we said, maximum area. So maximize, we know that's take the first derivative, right? Okay, so we're going to maximize that, but I can't really take the derivative when it's got both the L and the W in there. Okay, that's where this other function is going to come in. So it's going to be pretty nice actually, because I'm going to be able to say, oh, solve for one of these variables, substitute it in, and just work just with that guy. Okay. Oops, I didn't finish simplifying this. I'm sorry. 320 equals, what's 6L plus 2L? 8L, right? Okay, that's a better, more simplified. I don't know why I did that. Sorry about that. Okay, so in order to substitute this in to my area function, what I'm saying is I want to solve for one of these. Solve for one variable. And I'm going to substitute that into my area function. Area equals length times width. That formula that I know. Okay, that's what I'm saying I want to be able to do. Okay, so I can do that. Which variable would you like to solve for? I don't really care. I'm feeling this W guy. There's not a reason. You could totally solve for the L guy. It does not matter. But I just am like, okay, I'm gonna get the W by itself. So 320 minus 8L equals 4W. Okay, right, because I'm subtracting the 8L off both sides. Everybody knows how to do that. Okay, and then to get the W by itself, I need to what? Divide everything by 4. Okay, and I'm going to go ahead and swap this guy to the other side. So W equals 320 divided by 4. Well, 320 or 32 divided by 4 is 8, so that's 80. And then 8 divided by 4 is 2L. So I've got 80 minus 2L. That is that equation solved for one variable. Okay, and what am I going to do with that? I'm going to substitute it into the area formula. Well, the area equals length times width, right? That's what I'm going to substitute it into. And I'm going to put that where the W is. So right here, instead of W, I'm going to plug in that guy. So what I've got is area equals length times, instead of W, I'm going to write 80 minus 2L, right? That's the substitution step. Okay, now I have a function right here that I can work with. I'm going to go ahead and distribute that L through. I see it's, oops, my pencil lead broke on me. Okay, I see the L is in front of the parentheses, right? So, and I don't want to deal with this. I know I'm about to take a derivative, right? Because we want to maximize this. We want to find the maximum value. So I don't want to deal with that as a product rule. I want to go ahead and distribute that through. So A equals, this is 80L minus 2L squared. Everybody see that? Just distributing it through. Multiply that L through. Pass it out. It'll be okay. All right. This is my area function, and I want to maximize that. Okay. I keep saying I'm going to take the derivative. How do I know I'm going to take the derivative? Well, because we did that whenever we want to find maximums and minimums, right? Okay. And sure enough, that's what I'm going to do here. So let's take A prime. Take the derivative. And what's the exponent up here? This is a polynomial now, right? So I can use my power rule. The exponent is a 1. 1 times 80 is 80. Subtract 1 off that exponent. I get L to the 0. L to the 0 is a 1. I don't mess with that. That just goes away. Okay. Minus 2 times 2 is 4. L to the subtract 1. That exponent becomes a 1. I don't have to write it if I don't want to, right? Okay. Now I'm looking at this thing going, hey, that's actually kind of nice. I want to maximize this. So I'm going to, what am I going to do? What's the rule for finding a maximum? We take the derivative. What was the next step? Set the derivative equal to 0. Solve for your variable. I'm going to add the 4L over because it's negative. You could do it the other way, but you'll divide by a negative. That's fine. Okay. Divide by a 4 here, right? L equals 80 over 4. I'm getting a 20. Okay. So what we're seeing or what we're hearing here is that's a maximum length. Well, let's figure that out. Is it really? Okay. So let's go back to our function here, or function that we put together. And let me let me come here. It was A equals 80L minus 2L squared, right? Okay. And whenever I see this particular thing, the L squared was negative. So I know it's an upside down parabola, right? And so whatever value I find here is a maximum. And if you wanted to, you could go back and you could plug in into the original formula here, the function here. You could plug in a 20 and find out that value. You could also put it on your calculator and see, hey, what's the maximum there? Trace the graph, those kinds of things. But I'm getting L equals 20, and that would be feet, right? Because we're talking about linear feet. Okay. And so that's one of my dimensions, okay, is 20 feet. Am I finished? No, because the question asked me for, if you remember, find the dimensions of the fence and the area of the largest garden. So I'm not done yet. I need to find the other dimension. Well, somewhere up here, right here, I have this thing already solved for. Oops. Yeah, that was my I'm just making sure I'm on the right path. Yeah, this was my perimeter stuff, right? So up here, I already had this thing solved for W. So let me plug that in with an L. W equals 80 minus an L of 20, 2 times 20. Okay. So W equals 80 minus 2 times 20 is 40. W equals 40. Okay. So this is what I meant earlier by sorry. This is what I meant earlier by I don't care if it's really the length. We in our heads get length is the longer one, but it really doesn't matter. We could have just as easily called these sides like A and B. It doesn't matter. Okay. So one side is 20 feet, the other side is 40 feet. Okay. We know that length is normally longer than width. So if you want to switch those variables and make this your W and that your L, you can. We don't really care. What we care about is that this is what's going on. And the one that matters is the one I initially labeled as the L because he was one of those with $6, right? Okay. So that's what really matters for me there is that I'm only doing one length of 20 feet is $6. Okay. All the other lengths are going to be $2. So again, let me bring this picture over here. I already wrote all over the other one, so I want to. There's my picture. All right, that's what's going on. So we're saying, hey, one of these sides is 20. One of these sides is, all the other sides, well, the widths are 40. Okay. This guy happens to be the $6 guy. That's the way I measured him earlier. This guy is $2, $2, and $2. So let's do the math there and just kind of check ourselves and make sure that we're not going over our budget. Okay. So what I'm saying I'm going to do is 20 feet at $6. That's $120. Okay. And then this is 40 and 40 is 80 plus 20 is 100 feet at $2. Well, 100 feet at $2 is $200. And look at that. That will literally come out at exactly $320, which was my constraining factor, right? The owner of this company or this house only wanted to pay $320. So we were within budget if we make this 20 feet, $6, and all the rest, 40 by 20, make all the rest of the sides be $2. Okay. So we have our dimensions. It's a 20 feet by 40 feet. I still need the area. So what was the area for this one? Length times width. And we're saying we're going to use a 20 and a 40. And when we multiply the 2 times the 4, we get an 8, 2 extra zeros. 800. And when we do the inside here, that's no longer feet, right? That's square feet. So square feet, because we did feet times feet, that's square feet. Okay, so that's what's going on there. So have we answered the questions now? We have both the length and the width. 20 by 40. My dimensions are 20 by 40 rectangle. Okay, and my area is 800 square feet. So, yep, we answered all the questions and we stayed within our constraint, which is lovely. And that's what we're talking about, the maximum area. So, that was the optimization part of this, right? The maximum area that we can make for this amount of money that they're making me restrained on. The maximum area of that is 800 square feet. All right. So, what I'd like for you to do is think, well, what if the owner of this property said, 800 square feet's a little bit small. I kind of changed my mind. I'm willing to pay a little bit more money, but I really want 1,250 square feet. Okay. So that's that problem. We're done with it. But what if the owner comes back and says, I really want 1,250 square feet. That's just a little bit too small for me. I want to do that. I want to have 1,200 square feet, but I want to have the smallest cost possible. I don't want to spend a lot of money. So, what are they asking me to do there? They're asking me to minimize their cost, right? So, they want to know, what is the minimum cost? We're going to keep everything else the same. Okay, to build this fence. Okay, but I want the area. I stepped it out. I saw 20 by 40. I saw how small that is. It's really kind of small. I want a bigger garden. I want 12. I stepped it out. I want 1,250 square feet. Okay, so what are the new dimensions? And again, notice how the problem changed. Last time I was maximizing area. Now I'm minimizing the cost, right? Okay. We don't know what that minimum cost is yet. So they're kind of taking the constraint off of us as far as cost. But now they're putting a new constraint on me. That's going to be the area. Okay. Does that make sense? So it's flipping this thing around the other direction to see it. Instead of a maximum, I'm doing a minimum, but it's still the same process of optimization. Okay. So it's still that same thought pattern going into figuring this guy out. So that's what we're up to. Let's just see what we know. We're using the same two functions that we started, formulas that we had last time, because it's still a rectangle, right? Okay, I've still got length, I've still got width. These guys are still same dimensions, they're still 90-degree angles. All of that stuff is staying the same. But what we're saying is this inside space, we want that to be 1,250 square feet. Okay, so we know what's inside. You tell me what's on the outside now. Okay, while minimizing my costs. And by the way, minimizing the perimeter here, okay, is probably going to help minimize my cost, right? Okay, that's what we're talking about here. All right, so let's put up here what we know. The area is length times width, and we're saying that we're going to make that be 1,250. That's going to be a set number, okay? So that part is pretty set. I'm not going to mess with it any. Okay. Well, I might mess with that formula in a minute to get it the way I want it to be. But the owners of the property that I'm working on here, that I'm putting this fence up for them, they're setting that dollar or that space amount now. Okay. The other thing that I have is the cost function, right? So the cost function. But hey, hang on a second. That guy is totally set up based on what's going on with the other with the fencing materials, right? So the cost is totally based on the perimeter here. Okay. So we had a formula earlier. Let me find it. We had the perimeter of the rectangle 2L plus 2W. And then we said, we know that our cost here, this was my cost here, right? Was the 320. So the cost was the 8L plus the 4 times the W. Okay. Because we had 6 on the one, 2 on the other, 2 on the other, 2 on the other. This guy was $6. I'm not changing any of that information on us. Okay. All of that stays the same. So the cost function was 8L plus 4W. Okay, we found that already. I don't want to go back and redo it. It's the same process, but we already had that function. Okay, so we're looking at this, and now instead of taking the derivative of the area, we actually want to take the derivative of the cost. And I know that because I want minimize the cost, right? Okay. Now, the problem here is, I put C of L. It doesn't matter what function, but or what variable, but the problem is that I've got 2 variables there, right? And I've got 2 variables here, and we don't know how to take a derivative with 2 different variables floating around in there. So we're going to have to do the same thing that we did earlier, which is rewrite this area function in terms of, we're not taking a derivative, in terms of one variable. And again, I'm going to pick W. You could totally pick L. It does not matter. Okay. But the idea is get one of these variables by itself. So if I have L times W equals 1250, and I'm getting the W by itself, then what I want to do is divide by L, right? So I can do that pretty quickly and easily. Get the W by itself by just dividing. There it is. Okay. And what am I going to do again? Same thing I did last time. I'm going to substitute that in right there. And when I make that substitution, I will have W in terms of this L stuff. And I will get rid of that W, and I'm going to plug in this L stuff. So my new cost function looks like C of L. That's why I put that L there earlier, because I knew I was probably going to solve for W and have L's left over. 8L plus 4 times, but instead of the W, I'm going to put in this stuff, 1250 over L. So you got to make that substitution step. Okay. And all of these that we're doing like this, we're going to have the 2 different formulas, and one of them we're going to have to put in terms of just one variable and substitute in. So that's a pretty standard step there. Okay. So I've got that. Let me simplify this just a tiny bit. I've got 8L plus 4 times 1250 is, well, times 2 would have been 2500, right? Times 3 times 4 is 5000. 5000 over the L. Remember, the 4 is over the 1, so we multiply straight across the top, straight across the bottom. Okay, so here's my new cost function. And I don't really love the way that looks because the L's on the bottom. So I'm going to do one more little simplify step, and hopefully you know what it is. I'm going to move this L to the top, and hopefully you know how I do that. C of L equals 8L plus, I'm going to make that 5000 L to the what? -1. That's right. It's -1. Okay, so that's what I'm working with. That's my new cost function. Can I minimize that? That's what we want to do, right? Remember, that's my whole goal here is minimize the cost because they want a bigger fence, but they don't want to pay too much extra for it. So we're going to minimize the cost. And heck yeah, we can do that. We know how to do that. We're going to take the derivative, we're going to set it equal to 0, and we're going to solve. So if you would like to, please push pause and see if you can find the derivative of this function, c prime of L, and then come back and see me. Okay, hopefully you did that. And I am working my way through this process. I'm going to subtract 1 from that exponent. I multiplied already by the original exponent, and I've got a -2. So I think that your derivative function should be 8 minus 5,000 L to the -2. That's an L. Sorry, my L's are looking weird. Okay, tonight, I don't know why that's happening. L to the -2. And I've got the derivative. Okay, we need to, what was the next part of that? Set it equal to 0. Okay, I can do that. I'm going to, oh man, I don't like, oh, set it equal to 0. I don't like the way this is looking. So let me rearrange this just a tiny bit. I'm going to actually move the 8 over. It's going to make it negative, but I've got a negative on the 5,000, so I should be okay. And then here we go. Oh, I know what I was thinking. I'm thinking about this guy is actually, because it's L to the -2, I could rewrite him. That's what I was thinking. I could rewrite him with the L on L squared on the bottom. If you don't want to do that, then you can totally deal with this negative exponent in a minute by raising the thing to a -1/2 power. But I'm going to go ahead and move him to the bottom because I see that if he's on the bottom, I'm dividing by L squared. What I can do is multiply both sides by L squared and get him out of the denominator very quickly, right? So that's just what I saw to do. You don't have to do it that way. Um, you could totally deal with it as, I don't know why this pen's writing so light. Okay, you could totally deal with that negative exponent. I just don't like dealing with negative exponents if I don't have to. So I've got a -5,000 equals -8 L squared. And now to get that L squared by itself, I'm going to divide by the -8 again. I know. First I added it over or subtracted it off, and now I'm dividing again. Okay, so these negatives all go away, the 8s go away, and I end up with L squared equals 5,000 divided by 8, and I feel like that's going to go in nice and pretty, and indeed it does. I just punched it on my calculator. It's going to be L squared equals 625. Okay, so you can divide that guy out and see what you get. Um, Here is my calculator. So 625. All right. And then we're almost finished. I need to take the square root of that guy to get rid of the square. Remember that when you put in the square root, you have to plus or minus this. The square root of 625 is 25. If you're not sure about that, you can punch it on your calculator. Square root of 625 is 25. So L equals plus or minus a 25. But there's a little thing about this. We know that we are dealing with a fence line here. And are we going to have negative fence lengths? No. So we're only going to deal with the positive here, 25 feet. Okay. So last time we had a 20 and a 40. This time we have a 25. It's not that much different. But we do have a different value. So that's going to be work out for us. No problem. let's go back and plug this in somewhere. So if you'll recall, I had the formula W equals 1250 over L, right? I had solved my area formula for the W. So now that I know L is 25, I can totally plug in that 25 and I can come over here on my calculator and divide that because I don't want to do it in my head. 1250 divided by 25, I get a 50. So again, here my width is longer than my length, but I don't care. It doesn't really matter. What matters is that here's my thing. Nope, that's not it. I'm sorry. I'm looking for that picture. What did I do with my piece of paper? Oh, here it is. Okay. So I don't care which one of these is my length and which one of these is my width. What matters here is the L was the guy that I put the 6 on, right? So this length over here has to be a 25, which means this one's a 25, this one's a 50, this one's a 50. I drew my picture backwards. It's okay. All right. So those are my dimensions, 25 and 50. That's what the picture would look like, right? Okay. So I've got my dimensions. I'm going to make a 25 by 50 rectangle. Let's check our math and make sure that that gives me the square footage that I wanted. 25 times 50 is indeed 1250. Yay, that's good. That's what I was after. So that is the constraint that they gave me. 1250 square feet, right? That's what I was after. And now I need to make sure I've got my minimum cost. So I haven't put that together yet. I need to figure it out. Let me come back to my formula that I had. My cost formula was 8 times the L plus 4 times the width, if you'll remember that. Okay. Because the length was the one I put the 6 on, right? This was 6 plus 2. This was 2 plus 2 for the dollar for the cost. If you remember that. If you're not, go back and rewind it. So I'm saying 8 times 25 and 4 times 50. And again, if you don't like that my length is shorter than my width, you can flip those variables around and do it the other way. It will be fine. Okay, 8 times 25 is 200. 4 times 50 is 200. So $400. So actually it's not that much more, right? 320 to 400. That's just $80 more and they're getting a lot more square footage, right? So they had 800 square footage before. Now they're getting 1250, so that's a difference of 450 square footage. For only the difference between the 320 and the 400 was $80 difference. So for $80 more, they can get an extra 450 square feet. Probably my client likes that. That's what I'm thinking whenever I'm trying to figure out what their dimensions are and what their minimum cost would be. Okay. So that's all great and dandy, but those are very physical problems, very algebra-y problems, right? They're not business problems. There is some cost. Excuse me, I'm so sorry. Took off in the microphone. There is a little bit of cost that's here, but that's not really a business application. So what we would like to do is some business problems. So hang on just a second. I'm gonna get a call. All right, sorry about that. Just had a little tickle in my throat. I had to fix it. Okay. So we want to be doing some more business application type problems, right? So remembering that we want to maximize, in most cases, revenue and or profit. Those are the optimization problems. We're optimizing our profit. Here's your word problem. Example. You have a company that makes markers. Okay. Our company makes markers. Somebody in the back office has come up with a price demand function. This is absolutely the kind of problem you're going to see on your homework. Your price demand function is P of X equals 10 minus, and they give me this little decimal 0.001 X. Okay. Now, this is a negative linear equation the way it is. It's just the price right now. Okay. So I don't have a revenue function yet. So we're going to have to figure that out just a little bit. But the question for the thing says what price will maximize the revenue. Okay. So, and then they want to know, so what price? That's my constraint, right? So, in other words, if I sell my markers for 50 cents a piece, I might be able to sell a whole bunch of them, right? And I might make a lot of revenue. But if I sell the markers for $50 a piece, probably people are going to go, I'm not buying that. That's ridiculous. Okay. And then my revenue might not be very much. Okay. So maybe only like my mom will buy them or something. So nobody out in the real world's going to buy my $50 marker unless it, I don't know, does something amazing. Okay. So, um, I want to know what price is the good one for me to sell this at. I also want to know, okay, once I have that price, what is the maximum revenue? So can we go ahead and find the maximum revenue? So again, there's two things here that they're asking me for. And I'm going to see what we can do for this. Now, earlier in this class, we actually talked about how to come up with a revenue function. Hopefully, that's in the back of our databases somewhere. So remember to come up with revenue. Revenue is money in. What we do is we figure out what the price of our markers is going to be, and then we figure out how many we're going to sell, right? So if my price is $2 a marker and I sell 10 of them, then 2 times 10 is $20. I have now made $20. That's revenue coming into my pocket. All right. I still would need to, in order to find the profit, I would still need to subtract out cost, right? What did those markers cost me to make? Okay. But aside from that, this is how I come up with a revenue function. Okay. So I don't have a revenue function. What I have is my price function. And the price demand, that means that that's what people are telling me the demand is. Maybe my marketing people went out and did a bunch of surveys or something, but somehow I know that this is what price I can get based on how many I'm trying to sell. The X is the number of markers, right? So this is the price I can get. So what I want to know is what's my revenue. So my revenue function is going to be, and it's going to be revenue with X as my variable. The price function, okay, the price was 10 minus 0.001X times the number of those markers I'm going to sell. Well, how many are we going to sell? Well, I don't know. Um, maybe it's 2, maybe it's 10, maybe it's 500. I don't know. That's my variable, right? However many I'm going to sell. So the price changes based on how many I sell, and I don't know how many I'm going to sell. Okay. Well, looky there. That X is being multiplied by this whole binomial here. And I believe I can distribute that through and come up with what's going to be a fairly nice little, looks like a polynomial, looks like a power function to me, or power rule. Okay. So we like power rules. They're nicer to take than if I have to do product rule or quotient rule or chain rule or any of that stuff, right? Okay. So distribute that X through 10X minus 0.001X squared. Okay. And sure enough, that looks like something I can use my power rule on. And that's what we're going to do. Okay. The book actually has a little note that says, by the way, notice that my P of X needs to be greater than or equal to 0. Well, yeah. If I'm not charging a price that's greater than or equal to 0, then it doesn't make sense. But they're just trying to kind of say, you know, don't make it be don't make it be negative price or something like that. That's not going to work for me. Okay. Yeah. It also gives me a constraint for the number of them that I can sell. We'll talk about that in a second. I'll come back to that. Okay. So maximizing the revenue. Here's my revenue function. How do I maximize? Well, you take a derivative and you set it equal to 0. So everybody take your derivative, r prime of x. Okay. I'm going to go ahead and multiply that out. 10 minus 0.002x. And I got that 2 minus 1. So the exponent there is a 1. Okay. There's my derivative. And I'm going to take that guy and I'm going to set it equal to 0. Okay. This is the same stuff we were doing before. Set him an equal to 0. I'm going to make the x be positive because I don't like having that minus guy, especially with that big ugly decimal. So I'm going to add that to the other side. So I've got 10 equals 0.002x, 0.002x. Okay. And I need to divide that. And if you don't remember, whenever I divide by a decimal smaller than 1, it actually makes that number bigger, right? So whenever I come in here to divide 10 divide by 0.002, you're dividing by a number that's smaller than 0. It's like you're dividing by a fraction, right? And when you invert and multiply that fraction, this guy's going to get bigger. So don't be surprised or don't be like, oh, I messed up because we didn't. When I divide that, I get 5,000. Look at that. Okay. So x equals 5,000. All right. So, what's my maximum revenue? Where does that come in? It comes in at x equals 5,000. Okay. So I need to sell 5,000 markers is what I'm hearing. Okay. So if I sell 5,000 markers, I'm going to make a lot of money. Okay. Did I ask what's the price? Yes. All right. What's the price? That was the question. Well, how do I know the price? I'm going to have to put that 5,000 in here, right? The price was based on how many markers I sell. So I'm going to have to put in a 5,000. Let's figure it out. So P of 5,000. What price can I sell if I'm planning to sell 5,000 markers? Because that's going to maximize my revenue, and I'd like to maximize my revenue, please. 10 minus 0.001 times 5,000. Okay. Well, 0.001 times 5,000, what's going to happen there? The 0.001 is going to make that a lot smaller number, right? 5. Okay. So all of that is 5. So I've got 10 minus 5. That's my price. Or $5 per marker. That's the price where I can get my maximum revenue. They've done that survey. They know, okay, the market will hold this. The market will support if we do $5 per marker. We'll be okay. Okay. So we answered that question. What price do we need? We need $5. Okay. What's the maximum revenue? We haven't answered that. We said the maximum revenue happens at X equals 5,000, but we didn't find the maximum revenue. So let me come back in here. There was my revenue function before I marked it up. Okay. I want the maximum revenue. I want that in the revenue function, right? So that's why I'm going back to the original revenue function. Okay. So I can find the maximum revenue if I go back to the original function and do what? What do I need to do? Plug in 5,000. Yes, that's what I need to do because the X for the maximum is at 5,000. Okay, be careful here with this 5,000 squared. We're going to have to do that first because order of operations and all that good stuff. I probably could have gone back. I'm just looking at it. I probably could have gone back even a step before that and done this piece right here, because the reason I'm thinking that is because I already did 10 minus 0.001, right? I already have that price. So I could just say the 5 times the 5,000, but I already got it here. So we'll see what it is. It's okay. It's just a little bit more mathy and, 5,000 squared. Okay. I get a really big number, but remember when I multiply by this 0.001, that's going to make it smaller. Okay, that's better. Okay. And then I've got 10 times 5,000. Well, that's 50,000, right? Minus the 25,000. What is that? 25,000. That's how much revenue I have. Okay. So, that's just plugging it into the formula. Let me show you what I was just thinking so that it makes more sense, hopefully. Remember that the revenue function was, we got it originally, price times the number sold. So what I was saying, and I was thinking out loud, I apologize, was, hey, if I had $5 per my price and I know I need to sell 5,000 of those, then I could have, instead of doing this, which was just kind of a pain, I could have done 5 times 5,000. And sure enough, I would have gotten the same number, right? That would be less mathy, more straightforward way of doing it. So you could totally do that. It would be just fine. Okay, did we answer all of our questions? We have the price at $5. We have our maximum revenue at $25,000. Yes, we answered our questions. Okay, so hopefully everybody's okay with that. Does it make sense? Think about it, work through it, pause, rewind the video, whatever you need to do. Okay. All right. What about maximum profit for this problem? Same problem. We're not going to mess it up too much. But what if we want to maximize our profit? Now remember, profit is revenue minus cost. Okay, so we just dealt with revenue just a second ago, but in order to find my profit, I need somebody to go out and do, like I said before, keep track of my utilities, keep track of what I'm paying my people, all that kind of stuff. So let's assume that somebody in my finance office has been doing that and they've got a cost function for me. Okay. Now this one, the cost function, putting that together is a lot more complicated, because you really have to figure out how much it is per item, because X, remember, is the number of items I'm going to sell. So we don't really have a way for this problem to put that together, and it's a little bit more complicated. So hopefully if you're going to do some of those finances or finance classes or economics classes, you'll see that. Okay, so they tell me that this is my cost function, and the question that they want to know is, what is the company's maximum profit maximum profit Okay. And what should they charge per marker? Now, isn't that interesting? Because what that's telling me is the price to maximize my revenue was $5, but is the price to maximize my profit still $5? I don't know. That's the question, right? Okay, so and then if we're doing that, how many markers should we make? Okay, so there's 3 questions for this one. Okay, max profit, what should I charge for the markers, and um, what is my how many markers should we make at that price, right? To get the maximum profit. Okay, so let's figure out our profit function because we're trying to maximize profit. So profit equals the revenue function. Well, hang on a second. We already have our revenue function. It was 10x minus 0.001x squared. That was my revenue function. Everybody remember that? Okay. Minus the cost function. Well, the cost function is 5,000 plus 2x. Okay. So revenue function minus cost function. That's how we're putting together our profit function. We actually did this earlier as well, so hopefully everybody is okay. The big thing here is make sure, because we're subtracting, that we distribute that negative sign through. So profit function is 10x minus 0.001x squared minus 5,000 minus 2x. And I see that I can combine some like terms, so make it a little bit nicer. P of x equals, this is going to be 8x minus 0.001 x squared minus 5,000. All right, there's my profit function. Okay, first thing it wants to know, what's the maximum profit? All right, well, we haven't maximized profit yet today. So remind me how we find a maximum. Take the derivative, set it equal to 0, solve for x. It's always the same process, right? Okay, so hopefully you have this down by now. This guy is a polynomial, so I'm going to use my power rules. If you want to take this derivative without me, push pause for just a minute and see how you do. If not, I think it's 8 minus 0.002x, okay? Because the x here is going to go away. I subtract 1 from that exponent, it becomes a 1. And this minus 5,000, that's a constant, right? So the derivative of a constant is 0. So I've got my derivative. I'm going to set it equal to 0. I'm going to move the x guy over to make him positive. Okay, and I see again what I saw a little while ago. Whenever I divide by this decimal, it's a little bitty decimal that x is being multiplied by. I'm going to divide by that. And whenever I do it, that 8 would become a much bigger number, right? 8 divided by 0.002 is 4,000. So x equals 4,000. Okay. I can find my maximum profit at x equal 4,000. Okay, that's actually the third question that they asked me, right? The question was, how many markers should we make? So we're finding that answer first. So that's okay. Here it was 4,000 is how many markers I need to make. Okay. All right. I don't know the maximum revenue yet, but I should be able to go back and plug that guy in. And sure enough, find out what is my profit whenever I sell 4,000 of these guys, right? So my profit function was 8 times my x, I'm going to plug in a 4,000 minus 0.001 x squared. I'm going to plug in my 4,000 minus the 5,000. That was my profit function, right? Excuse me. So that I mean, I got to do some plugging in. It's not going to be pretty, but it's not that bad. I've got a calculator. So 8 times 4,000 is 32,000. I can do that one in my head. This one's not so nice. So 4,000 squared is a big number, really big number, times 0.001 is going to make it a little bit smaller. So that's minus 16,000. Okay, minus the 5,000. Okay, so 32,000 minus 16,000 minus 5 is 11,000. And that is dollars. That's my profit, my maximum profit. Now, hang on just a second. Let me stop for just a second and talk. What we found a minute ago was for the maximum revenue, maximum money in, I needed to sell 5,000 markers, right? Okay. And when I did that, I was making $25,000 in revenue. Okay. But what we're seeing here is we're now seeing, but my maximum profit comes out when I sell 4,000 markers, right? That's markers. Okay. My maximum profit is happening when I sell 4,000 markers. Okay. So the question becomes, how can that be true? Well, it's because what I showed you earlier, let me draw this picture kind of here. If my revenue function is a parabola and my cost function, what was my cost function? Hang on, let me find it. Sorry. My cost function was an upward sloping line, okay, because it was 5,000 plus 2x, right? Okay. Earlier, we found the maximum revenue, okay? That was just the vertex. But what we're seeing now is actually my maximum profit. Here's my revenue. Here's my maximum profit. So they're saying, well, you won't make the most possible money in as you can, but down here your costs are a little bit less. It's like to make these extra 1,000 markers, it's just enough additional, that marginal kind of thing is too much more to make a lot more. It makes a lot more costs. So my profit here is less. The gap here is smaller, is what they're telling me. Okay. So this is the situation I was talking about earlier. Well, maybe sometimes we don't want to maximize revenue. Sometimes we are much more interested in maximizing profit. Okay. So that's not $25,000, but that's $11,000 profit that's left over. That's money in my pocket. Okay. So that's after I paid off all my costs, right? After costs. That's what profit means. Okay. So sometimes that's what we want to do. Okay. And that's kind of the situation that's happening here. All right. So what is my maximum profit? Maximum money left in my pocket is going to be 11,000. Okay. And then the last question says, what should they charge per marker? Oh, hang on a second. That means I got to go back to that price function, right? Okay. So my price function, if you'll remember, scoot up, was lowercase p, not capital. And profit is always capital P, right? Okay. So lowercase p of x was 10 minus 0.001 times x, right? Okay. And if I'm trying to maximize profit, we said, well, we're going to use x equals 4,000, right? For maximizing profit. That's what we had up here, 4,000 markers. So now we want to find out what price we need to charge for the 4,000 markers in order to maximize my profit. 10 minus 0.001 times 4,000. Again, this is going to be 10 minus 0.001 times 4,000. That's multiplied, so that's going to make it a smaller number. That's a 4. 10 minus 4 is $6. Okay. So in order to maximize my profit here when selling these 4,000 markers, I need to set my price at $6. Okay. And that is because remember at the earlier in the semester, we talked about this. The price demand function, it depends, right? If I had, remember that example was box of oranges. If I have a box of oranges, I might want to sell it for $20, but somebody else might not want to buy it for $20, right? I always want to sell for more if I can, but the buyer always wants to pay less. Okay. So that's that market equilibrium coming in there. And what it's telling me is, if you want to sell 5,000 markers, you can only charge $5 a marker. Okay. But if I don't put quite so much of a supply out there, a little fewer markers, okay, 4,000 instead of 5,000, I can charge a little bit more because it's a little bit harder to come across those markers, right? That's like earlier when I said, well, I might want to charge them $50 a market, but the demand's not going to be there, right? Who's going to buy that marker at $50 a marker? Not many people are going to do that, right? Okay, so we have answered all three of those questions. We are good. Okay. Is that all right? All right. One more question, and we're going to stick with this marker idea. One more example, I should say. Okay. It's like a continuation. What if, out of the blue, the government decides, I can't write, decides that they're going to tax all office supplies. Okay. And my markers are now going to be taxed. My markers at $2 a marker. That's a lot of taxes whenever I'm only getting $5 or $6 a marker, right? Okay. So the government's wanting to tax me, okay? $2 a marker. Oh my gosh, that's a lot. Okay. So what is that? First of all, that's an additional cost. Does everybody understand that? This is an added cost. Okay. And most of the time, we might absorb part of that tax, but we're not going to absorb all of that tax. We're probably going to send some of that on to the customer, right? Because I can't afford to lose $2 per marker. If I lost, and I'm only making $11,000 over the profit, if I lost $2 a marker at 4,000 markers, I lose $8,000. If I'm only making 11,000 in profit, that only leaves me 3,000 in profit. That might not even be worth staying in business for, right? Okay. So I could get taxed out of business at this point. Okay. What's the added cost and what's my maximum profit now? Okay. That's what I want to know. So things like this can make lots, like it might seem like, oh, it's only $2 a marker, who cares? But that's a lot. It's a big percentage of my cost or of my price for one thing, and second of all, like that can really cause some havoc. So first, let's first let's adapt our cost function. Okay. If you remember, my cost function was 5,000 plus 2x. Okay, that was my cost function. But now they're saying they're going to charge me an additional, or I'm going to have a cost of $2 per marker again. That's another 2x. Does that make sense? Okay, $2 per marker. So my new cost function, it looks similar to the last one, to 5,000 plus 4x. That's my new cost function. That's the only thing that's changing. Okay. Well, okay, if that's the only thing that's changing, let's go back. We're wanting maximum profit, so let's go back and write my new profit function, right? Because the profit is money in minus money out. So if they change my money out, that's what this is. That's money I have to spend. Then my profit function, my capital P, is my revenue function. Well, that didn't change any, right? At least that didn't change. 10x minus 0.001 x squared. Okay. That's still my revenue function. But now I have to subtract this new cost function, right? So minus 5,000 plus 4x. And if you see that we're going to have to distribute that negative and you want to do it in one step, go for it. Okay. I'm just showing all the steps here. So now my new profit function starts out the same, but I've got minus 5,000 minus 4x. Okay. And when I come in here and I want to combine these two like terms, I see, oh, earlier I had an 8x when I finished this, but now I'm only going to have what? 6x, Dr. Webster. That's right. So again, it's going to change my profit function. Okay. And there's just nothing I can do about that. The government charged me that money. I've got to put it into my cost function because I'm going to have to pay it. And then that is going to affect my profit. Okay. It just is. Absolutely. All right. So the question was the same starting out though. So we've got our added costs. So that's $2 per marker or 2x, right? That's what we just figured out. Okay. I don't know about max profit yet, so let's do this process again. Again, if you want to pause, push pause so you can find your own derivative and then push play. That'd be great. Take the derivative. It's going to be similar to what we had before, but now it's 6 minus 0.002x. Okay. Subtract the 1. Subtract the 1. And again, that 5,000, it doesn't matter because the derivative of a constant is a 0. Okay, there's my derivative. We're going to take that guy. We're going to set it equal to 0. Same process. Hopefully you're getting really good at this process. Take that, set it equal to 0. Solve for x. Okay, I'm going to have to divide by the 0.002 again. Okay, but remember, whenever I divide by a really tiny decimal, it actually makes my number bigger. 6 divided by 0.002, and I get 3,000. Last time I think I got 4,000. I did. Okay, so I'm going to have my maximum profit is going to happen at 3,000 markers sold. Okay, that's what's going on there. Okay, notice that my number of markers I'm selling went down. Okay. And unfortunately, that means that probably my profit's also going down, right? Because I have this additional cost that I've got to deal with, right? So I've got a $3,000 or 3,000 markers is what I want. Again, you can always plug that guy in and see. I need to go back and figure out a couple of things. I would like to know what is my maximum profit. So that's the question that was actually asked. So that's capital P. I'm putting in a 3,000 this time. I am going to cheat a little bit. Oh, I can't cheat because I don't have my price. Let me come back here and figure out the price real quickly. Sorry. Because I want to cheat and just say price times the amount sold. So I can't do that until I come here. So that's not my price function. Stinker. What was my price function? My price function was lowercase p of x. Get this out of there so it's not confusing. Lowercase p of x was 10 minus 0.001x, if y'all remember. And what we're saying is, well, what if we had sold 3,000 of these markers? What is the market going to do for me? Well, it's fewer markers. So let's think about this for just a second. Fewer markers on the market means the price is actually going to go up probably, right? So let's see about that. It's going to be 10 minus, well, maybe you can see by now, this is going to move over 3 decimals basically, right? 10 minus 3. If you're not sure, let me show you it on the calculator. 10 minus 3. So $7 for these markers. Okay. Now, interestingly enough, what did I charge at my max profit? I charged $6 earlier when I was getting my max profit, right? So the government's charging me $2 extra, but I'm only passing $1 of that on to the customer here, right? It's only $1 more than what I had before. That's because a lot of times if we pass the entire $2 on, what we would see is we would lose more of the market, right? Okay. At $8 a market, we'd probably only be able to sell 2,000 markers. $8 per market at $8 per marker. So we might not want to pass on the entire tax to my customers, is what I'm saying. Okay. A lot of people say, oh, just pass it on to the customer. Sometimes the market won't bear that. So you got to watch out. Okay, so my profit here was the price, which we just said was $7 per marker, times the number of, oh, that's my revenue. Stinker. Okay, I guess I could go back to the profit function that I had up there, but let's go ahead and do this. It's okay. The 3,000, okay, minus the cost function was 5,000. Let me just find this real quickly. 5,000 plus 4 times 3,000 is 12,000, right? So 5,000 plus 12,000 is 17,000. The cost for me to make 3,000 markers minus 17,000. Yep, I think so. I'm going to have to figure that out. We'll go back and do it the other way just to make sure I didn't make a mistake. 3,000 times 7 is 21,000. Still a lot. Minus the 17,000. I lost a lot of money. I think it's only $4,000 now. Yep, I think it's only $4,000. So my profit now, even passing $1 of that cost along to the to the consumer, my maximum profit went from $11,000 profit to only $4,000 profit. Okay, so let me do it the other way just to make sure everybody's with me and I didn't make any crazy mistakes. So the profit function was, the actual profit function was 6x minus 0.001 x squared minus 5,000. Okay, that was what we came up with for the profit function earlier. Okay, and we're trying to find the profit of 3,000 markers. 6 times 3,000 minus 0.001 times 3,000 squared minus the 5,000. Okay, so maximum profit with 3,000 markers is, let's see what we got. That's 18,000. This guy is 3,000 squared. I'm very sure it was okay, but I just want to double check. Times 0.001. So that's minus 9,000. Yep. And minus the 5,000. So 18,000 minus 9,000 is 9,000 minus the 5,000. I've got $4,000. So that's a confirmation. No matter which way I did my profit function, with the $2 extra taxes added on there, with my prices, my cost function, all the costs that I have, all that kind of stuff. Even marking the markers up an extra dollar, $7 a piece. That's what we decided it would cost. Even doing that, I've got less than half of the profit that I had before, and that is really, really, really sad. Okay, that's going to hurt me a lot. Um, yeah. So anyway, just some stuff to think about there. One added cost can really cut into your profits. That's what you should get out of that. Also, notice that even though the cost went up by $2, we did not pass that whole entire $2, but we still lost a lot of profit. If you had if you had put the whole profit, I'm sorry, if you had given the whole tax to the people, to your customers, this would have been $8 a market. You would have only been able to sell 2,000 markers at that price for your max profit. It would have been much worse. Okay. So, just real quickly, what are some other things that we can use this optimization type stuff for? All kinds of stuff. Maybe if you were if you had a business, and let's say your business is that you're going to go out and you're going to give lectures, or you're going to give some kind of seminars or talks, um, how can I figure out what kind of price I need to pay or charge for my seminars? Okay, well, that's going to depend on the market, right? And I would like to maximize the money I bring in, okay, and probably maximize my profit or my revenue, and reduce the amount of cost, right? Minimize the costs. If one of my cost is, I don't know, storage fees or something like that, then depends on the side of the coin you're on, right? If I'm the consumer, I want to minimize my storage fees. But if I'm the company that's renting out my storage units, I would want to maximize the rent that I can charge, right? So, all kinds of maximizing and minimizing things go on here. All of that is part of the optimization process, and that you're going to see in your homework. So, take a look at the homework. Let me know if you have any questions. That's it for optimization. Thanks. And let me know if you have questions. Thanks. Bye.